We will now discuss thin-walled pressure vessels. Thin-walled pressure vessels are containers designed to hold fluids or gases under pressure where the thickness of the wall is much smaller compared to the vessel's radius. Typically, if the vessel radius to the thickness ratio is greater than or equal to 10, then it can be classed as a thin-walled pressure vessel. More specifically, if the R by T ratio, i.e. the vessel radius to the thickness ratio is equal to 10, then the result of thin wall analysis will determine the stress, which is approximately 4% less than the actual maximum stress within the vessel. If the R by T ratio is less than 10, then this error will increase. In the case of thin walled vessel, the stress distribution throughout its thickness is considered not varying significantly. Hence, we assume that the stress distribution within the thickness is uniform. Using this assumption, we can analyze the state of stress within a thin walled cylindrical or a spherical pressure vessels. A cylindrical tank carrying gas or fluid under a pressure small p is considered to be subjected to tensile forces that resist the bursting forces developed across the longitudinal and the transverse sections. Now we know that the fluid exert pressure in all the directions. Hence, we have a bursting force developed across the transverse and longitudinal sections. Consider a typical longitudinal section AA through the pressure-loaded cylinder in the figure A. A free body diagram of half a cylinder isolated by the cutting plane AA is also shown next to it. From our elementary knowledge, we can say that within a small differential area, the force dF will be equal to the pressure P times dA, where dA is the area of the element of the cylinder located at an angle theta from the horizontal diameter. dA will be equal to the longitudinal length L times d by 2 theta. Since we know that the length of the arc S is equal to radius times theta, hence we have d by 2 times theta, considering the differential length of this arc, and that is multiplied with the length L, and we get the area dA. Thus, the differential force on this element is equal to small p times L times d by 2 d theta. Now, this differential force is actually acting all along this semicircle. Hence, we can actually sum the contribution of all the small differential areas. One thing to remember is that this similar force will act on symmetrically placed element on the other side of this vertical center line. Now, this small force will have a component in the horizontal direction and in the vertical direction. The horizontal components of the small differential elements will cancel out with the horizontal component of the differential elements acting on the left hand side of the vertical line. Thus, we would be left with the vertical components of the differential force is dF. The vertical component of the dF will be rho L d by 2 d theta into sine theta, keeping in mind that theta is the angle of this differential area with respect to the horizontal axis. So small p times L d by 2 d theta times sine theta, and if we integrate this along the semicircle, which is 0 to pi, we will get the force F equal to small p d times L, where d is the diameter of the vessel and L is the longitudinal length of the vessel. Now, it is clear that this total bursting force, what we call F is equal to small p dl, would be resisted by the forces P on each cut surface of the cylindrical wall. So, applying the vertical equilibrium of forces, we have F is equal to PdL is equal to 2 times P. And from there, we can get our P equal to small p dl by 2. Now, this P can be divided by the area of this cut surface, which is T times L, and we will get the stress in the longitudinal section that resists the bursting force F. This stress, called as the tangential stress, would come out to be equal to P d L divided by 2TL. LL will get cancelled and we will get sigma T is equal to PD by 2T. The reason this is called tangential stress is that it acts tangent to the surface of the cylinder. Other common names are circumferential stress, hoop stress, or girth stress. Now, if we consider this other free body diagram of the transverse section, we will find that the bursting force acting over the end of a cylinder is resisted by the resultant P of the tearing force acting over the transverse section. We can find an analogous formula for the bursting force F. Now, one important thing to appreciate in this formula is that the bursting force F might be acting on the whole semicircle, but its magnitude is equal to the pressure times the normal area of the cutting plane, i.e., the area d times L. In a similar manner, the normal area for this transverse section will be equal to pi d square by 4 times P. Pi d square by 4 is the area of the normal transverse section. Thus, again, we can equate the bursting force F with the force P resisted by the resultant force of the tearing forces. P will be equal to sigma longitudinal stress times pi dt, where pi dt is the approximate area of the transverse section of the cylinder. Thus, pi dt times sigma L will be equal to pi d squared by 4 times P, and we will get the longitudinal stress equal to PD by 4T. Sigma L is called longitudinal stress because it acts parallel to the longitudinal axis of the cylinder. It is important to see that the longitudinal stress is half of the tangential stress. Therefore, If the pressure in the cylinder is increased to the bursting point, then failure will occur along the longitudinal section or the longitudinal seam of the cylinder. Analogously, we can easily derive the expression for stress in the wall of a spherical pressure vessel. The bursting force F will be equal to P times pi d square by 4, which will be resisted by P distributed across the thickness of the vessel. Again, pi dt will be compared to small p times pi d square by 4, and we will get sigma is equal to pd by 4t. This equation is similar to the longitudinal stress in a cylinder. Now, in order to understand it further, we shall discuss an example. A cylindrical pressure vessel has an inner diameter of 4 feet and a thickness of ½ inch. We are asked to find the maximum internal pressure it can sustain so that neither its circumferential nor its longitudinal stress components exceeds 20 ksi. The second part is that under the same condition, what is the maximum internal pressure that a similar sized spherical vessel can sustain? So as we said, in the case of cylindrical pressure vessel, we have the maximum stress equal to PR by T or PD by 2T. So this is our tangential stress. Instead of diameter, we can have thickness. So we are given the longitudinal stress component 20 ksi, plugging the values, small p 20 is equal to small p times 24 inches, which is coming out from the diameter of 4 feet, divided by ½ inch thickness. And plugging the values, we get p is equal to 417 psi. Similarly, the stress in the longitudinal direction will be half of the tangential stress, which is 10 ksi. The second part of the question is saying that under the same condition, what is the maximum internal pressure that a similar sized spherical vessel can sustain? So in the case of spherical vessel, again, we can use the formula derived earlier, and we get the pressure P is equal to 833 psi.